Hi there. Welcome to the periodic table simulation. Today you will learn how elements are organized in the periodic table according to similar properties and how it can be used to predict an element's behavior in a chemical reaction. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect, then let's get started with your first mission. Find the lockers and open one of them. Raise your lab pad for more information. Find a lab coat inside the lockers and pick it up. Just click to interact. Now find a glove box and put on some gloves. Then put on the safety goggles. Raise your lab pad for more info. Enter the lab. You're part of an exciting mission today. We're in the process of preparing a lab tour for students who want to learn more about the periodic table, and we urgently need your help. Some bricks in our periodic table wall have fallen out and need to be correctly placed back into the wall. Will you help us figure out where they belong? Click Continue if you're up for the challenge. Before we start the mission, we need to bring you up to speed with some important knowledge about the periodic table. Have a look at our periodic table wall. Isn't it beautiful? The Russian chemist Dmitry Mendeleev was the first one who created a table that helped derive the properties of different elements. The same idea has been used to develop the modern version of the periodic table, as you can see it here, which is an important tool for many chemists, nuclear physicists and other scientists worldwide. When you move closer to the periodic table wall and hover over the different boxes, you can see the full element names. Click on the periodic table wall and explore it further. Raise your lab pad when you are done. Are you done exploring? Great. Then let's carry on with your mission. We can sort the elements into three large classes with similar properties: metals, nonmetals and metalloids. Look at the periodic table wall, or click View Image, to see which colors represent the different element classes in the periodic table. Click metals, nonmetals and metalloids in any order and I will tell you about them. Click Continue when you feel ready to answer a few questions about the differences. Metals are elements that are shiny, ductile, and good conductors of heat and electricity. On the periodic table wall, you can see all the metal elements in blue on the left side of the table. Nonmetals are elements that appear dull and are poor conductors of heat and electricity. On the periodic table wall, nonmetals are shown in green and are located on the right side of the table. Metalloids are, like a metal, which means that they conduct heat and electricity moderately well, and possess some properties of metals and some properties of nonmetals. One famous example is silicon, which acts as a semiconductor. Metalloids are shown in red in our periodic table wall. You can check out the Theory tab on your lab pad at any time to read more exciting facts about the three main element classes of the periodic table. Click on the highlighted labels on the periodic table wall to learn more. Elements in the same period have the same number of electron shells and tend to have similar properties. Thus, it is relatively easy to predict the chemical properties of an element if one knows the properties of the elements around it. A new row, called a period, is started when a new electron shell has its first electron. Elements in the same group have the same electron configuration in their valence shell. This gives all elements in one column, called a group, very similar properties. We will learn more about it later. To which of the three main chemical classes does mercury belong to? Don't forget you can read the theory page, look at the periodic table wall, or look at the periodic table in the media tab if you are in doubt. Absolutely. Mercury, also known as quicksilver, has the symbol Hg derived from its former Greek name hydrargyrum. Alchemists considered it close to gold and therefore named it Mercury, after the planet closest to the Sun. All metals but Mercury are solids at room temperature and normal pressure. In contrast, non-metals exist as solids, liquids, and gases in the same conditions. To figure out where the boxes that have fallen out go to in the periodic table wall, we need to perform a couple of experiments. Luckily we have all chemical elements in their pure form here in the lab. What kind of experiment would help you categorize some of the elements? That's right. Testing the metallic character of the elements including shininess, electrical conductivity, and ductility, will help us to categorize the elements into metals and non-metals. Click on any of the fallen element boxes to transfer them to Workbench 1. Go to Workbench 1. You can see one sample of each of the elements we need to correctly assign to the periodic table in front of you. Based on their phase of matter and what you already learned, which of the elements is clearly not a metal? That's right. Neon is gaseous at room temperature and normal pressure. We know that none of the metal elements exists as a gas under these conditions. Observe the shininess of the elements. Use the forceps. Which of the elements you tested doesn't have a characteristic metallic appearance? Well observed. Phosphorus doesn't appear shiny. We saved your observation in the logbook. Dr. 1 has also tested other metallic properties such as ductility and electrical conductivity. You can see the results of all the tests on the screen to your left. Click on the screen to your left to check the results. Based on the results of the first test, you can now categorize the remaining 4 elements into metals or non-metals. In our periodic table wall, metals are shown in blue and non-metals in green. Assign the correct color to each element box, blue for metals, green for non-metals. Click a box to switch its color. Raise the lab pad when you're done. Have you finished assigning the colors? Well done, buddy. You correctly identified the metals among the 5 elements. The next step is to find the position of the metal elements in the periodic table. For this we can make use of a common analytic procedure, called a flame test. It can be used to distinguish different metal ions depending on the emission spectrum that is produced when the element is introduced into a hot flame. More specifically, when a metal ion solution is held into a flame, heat will excite the valence electrons that emit a certain wavelength in the visible light spectrum when falling back to their original state. Most metal ions therefore have a characteristic and known flame color when applied to a flame test. I prepared 3 solutions of ionic metal salts to test our metals of interest, namely sodium chloride, copper chloride and calcium chloride. You can find them in front of you on the workbench. Find the tool to hold the metal ion solution in the flame without burning your fingers. Clean it with hydrochloric acid and then water. Hold the wire loop into the flame of the Bunsen burner to check for residual ions. It's important to clean the wire loop and check before testing the first sample if all traces of ions from previous experiments have been removed. Also, make sure to clean the wire before testing a new sample. Dip the wire loop into the calcium chloride sample and hold it into the flame. Observe the color of the flame. Note your observation in the logbook on the computer. Dip the wire loop into the sodium chloride sample and hold it into the flame. Observe the color of the flame. Note your observation in the logbook on the computer. Dip the wire loop into the copper chloride sample and hold it into the flame. Observe the color of the flame. Note your observation in the logbook on the computer. Amazing. I think you managed to get clear result from the flame test. Well done. As you remember, I told you before, when a metal ion solution is held into a flame, the heat of the flame will excite the valence electrons that emit a certain wavelength, or you could say color, in the visible light spectrum when falling back to their original shell. Let's compare this with the flame colors that are known to be produced by some of the elements. What are the different colors caused by that we can see in the flame test? That's right. The characteristic flame colors are caused by electrons that were excited by the heat falling back into their original shell. Put the wire loop back. Go to the periodic table wall. Click on the Flame Test button in the control panel on your left. In this representation of the periodic table, you can see the known flame colors for each of the elements. Now it's your task to compare the results of the flame test with the known color to assign the first 3 metal element boxes correctly. You can check the results from the flame test anytime in the Media tab. Click Continue when you're ready to assign the boxes. Go back to the periodic table mode showing metals versus non-metals. Assign calcium, sodium and copper correctly to the periodic table wall. Raise your lab pad when you are done. Have you finished assigning the elements? Well done. You placed the 3 metal elements correctly in the wall. Most of the groups in the periodic table have a common naming. For example, the elements in group 17 are called halogens, whereas elements in group 18 are known as noble gases. Let's learn a bit more about those different element families and their names. Go back to the overview and click on the Element Families button in the control panel. Members of the same element group usually share similar properties. Transition metals, for example, are located between group 3 and 12, have a specific electron configuration characterized by an incomplete d subshell, which gives them some exciting chemical properties. Check them out in the periodic table wall. They are shown in purple and are in the middle of the periodic table. Similar properties within one element group often arise from the same number of valence electrons. The number of valence electrons of non-transition metals, also called main group elements, can easily be found by their location in the periodic table. This periodic table shows the valence number of the elements. Let us just talk about the octet rule, and how each atom strives to bond with another atom to form chemical bonds with 8 valence electrons. The valence shell is the outermost layer of an atom. Electrons in this shell are called valence electrons. The tendency of atoms from main group elements to form chemical bonds in such a way that each atom obtains 8 valence electrons is described by the octet rule. Having 8 electrons in the valence shell is a particularly stable state with the same electronic configuration as a noble gas. Don't forget you can check out the Theory tab on your lab pad at any time to learn more about valence electrons and the octet rule. Chlorine is part of the element family halogens, which are also known as salt formers. How many valence electrons does sodium have when forming an ionic bond with chlorine? As you remember, valence electrons are the ones in the outermost shell. Click View Image to look at the periodic table. How ironic, no wait, ionic. When forming an ionic bond with chlorine, sodium gives up 1 electron to chlorine, resulting in a complete octet of 8 electrons in the outermost shell, just like an octopus has 8 arms. However, when not in a compound, sodium only has 1 valence electron according to its location in group 1 of the periodic table. Based on what you know about their location in the periodic table, what do cesium and chlorine react to? Click View Image to look at the periodic table. Absolutely. With the exception of transition metals, all elements in the same group have the same number of valence electrons and therefore the same bonding behavior. As in sodium chloride, cesium donates its 1 valence electron to chlorine when forming a bond to fulfill the octet rule. Which group of elements have a full octet of electrons? Click View Image to look at the periodic table. That's right, all elements that belong to the Nobel gases, with the exception of helium, are characterized by 8 electrons in their valence shell and therefore a complete octet. Besides finding the number of valence electrons of a specific element by looking at the periodic table, one can also find helpful information about the oxidation state. This number is defined as the formal charge on the atom if all bonds were assumed to be fully ionic. Knowing the oxidation number or state is very useful, for example, when balancing reduction-oxidation reactions, also known as redox reactions. This periodic table shows the oxidation states of the elements. Applying the trends of oxidation states in the periodic table, what is a likely oxidation state of chlorine? A simple rule to remember is the oxidation state is for unmixed atoms the same as their charge. Click View Image to look at the periodic table. That's right. There are other known trends in the periodic table. This info will help us to assign the remaining 2 elements, phosphorus and neon, to the periodic table wall. Go to the hollow table. On the hollow table in front of you, you can observe the atomic radii of some elements within the same group, which are lithium, sodium, potassium, rubidium, cesium, and some within the same period, which are potassium, calcium, scandium, titanium, vanadium. On the dashboard of the hollow table, you can also see the electronegativity and ionization energy of the element being shown. Let's see if you can determine some common trends. Go through the definitions of the different chemical properties. When you are confident that you know, you can press continue. The atomic radius of a chemical element is a measure of the size of its atoms, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding shells of electrons. Electronegativity is a chemical property that describes the tendency of an atom to attract a shared pair of electrons towards itself. An atom's electronegativity is affected by both its atomic number and the distance at which its valence electrons reside from the charged nucleus. The ionization energy is the minimum amount of energy required to remove the most loosely bound electron, the valence electron, of an isolated neutral gaseous atom or molecule. All good to go then. As always, you can check out the Theory tab on your lab pad at any time to learn more about different element properties. Explore the different periodic trends on the hollow table. Use the control panel to your right to switch to another element. Are you done exploring? Great. You can view a table of the properties for the elements you looked at in the Media tab. Let's carry on with your next challenge. On the control panel on the wall, you'll also see a bunch of arrows. They show the direction of a trend, from a lower to a higher value. For example, an arrow pointing to the left would mean that this property tends to decrease when the group number increases, and vice versa. The direction of the arrows are not correct at the moment though, and each of them can be clicked to switch direction. It's up to you to get it right. Assign the arrows according to the trends that you observed and click Submit. You can anytime explore more on the hollow table to validate your result. Well done. You managed to find the main trends in the periodic table. Have a look at the image on the lab pad to see a summary of the different trends. What do you think is the reason for an increasing atomic radius within one group? Genius. Increasing the number of electron shells within one group directly influences the atomic radius of the elements. What do you think is the reason for a decreasing atomic radius within one period? Correct. The atomic radii gets smaller as we move up in group number within a period because no additional shell is added and more protons are present that draw the electrons to the core. When moving from left to right across a period, ionization energy is increasing. By which other trend is this caused? Click View Image to look at the atomic trends in the periodic table. That's right. The more tightly bound an element is, the more energy is required to remove an electron, and the ionization energy therefore increases when the atomic radius decreases. Electronegativity increases in the same manner as ionization energy because of the pull exerted on the electrons by the nucleus. Equipped with this knowledge about trends in the periodic table, have a look at phosphorus and neon and see if you can find any clues based on their chemical properties. Observe the properties of phosphorus and neon on the hollow table. Raise the lab pad when you're done exploring. Are you done exploring? Think about what you learned about trends in the periodic table and apply your knowledge by assigning the last 2 missing elements to the periodic table. Remember that you can always go to the Theory or Media tab to find the Explore the main trends in chemical properties again. Go to the periodic table wall. Go back to the periodic table mode showing metals versus non-metals. Assign phosphorus and neon to the periodic table. Raise the lab pad when you're done. Have you finished assigning the elements? You're a rock star. You have successfully assigned all fallen out elements in our periodic table wall. It seems we're all set up except for the atomic number. Let me unlock it in our periodic table wall. Have a look at the numbering in the periodic table. In the standard periodic table, the elements are listed in order of increasing atomic number Z. What do you think the atomic number represents? Spot on. The atomic number Z represents the number of protons and is fixed for every element. In contrast, the number of neutrons may vary, which creates the different isotopes for each element. Together, protons and neutrons make up the atomic mass. Note that in the periodic table, we can see the atomic weight, which shouldn't be mistaken with the atomic mass. The atomic weight, also called relative atomic mass, is defined as the average mass of all isotopes of an element as they are naturally occurring on Earth. The atomic mass is, therefore, a whole number, whereas the atomic weight would usually have several decimals. Right on time, just before our visitors arrive. I heard that the first visitor is already on her way. Now that you are an expert on the periodic table, I'm sure you can answer her questions. Wait for Lucy.
Hey there, I'm so excited to be in a real lab for the first time. I want to become a scientist one day. Chemistry has always fascinated me and I have a million questions. Can you tell me what the green color here in the periodic table stands for? Click View Image to look at the periodic table. That's really interesting. Krypton is my favorite element. Ever since I watched Superman for the first time. What's up with the other elements that are in the same group as Krypton? Do they have anything in common? Click View Image to look at the periodic table. Ah, that makes a lot of sense. According to what I learned at school, the same number of valence electrons also means similar reactivity and bonding behavior. We also just covered electronegativity in class and I heard it's something that one can estimate from the periodic table. Which is the element with the lowest electronegativity? Click View Image to look at the atomic trends in the periodic table. Wow, there are so many things one can see in the periodic table. Thanks a bunch for answering all my questions. I'm even more convinced now to sign up for a chemistry undergrad program.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.